Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So I'm very pleased today to introduce Wayne Stark. Wayne is a professor in the Department of Electrical and Engineering and Computer Science at the University of Michigan, where he has been since 1982. He's a fellow of the IEEE and has won the Milcom Technical Achievement Award, and he's got interests in coding and modulation for wireless systems and broad ultra-wideband networks and low energy, and you'll hear about some of that work today. Wayne?
All right, thank you, Phil. Okay, so I'm going to talk about energy and bandwidth efficiency in wireless networks. Okay. Okay, so I'll give you an introduction and background, and we'll describe the physical layer, devices, the network layer that we're going to use, the models for those. We'll talk about the performance measures, and then we'll give you some results. Okay, so the standard communication problem involves transmitting information from a source to a destination. Okay, and the relevant parameters are the data rate that the source has. The information from the source is encoded, modulated, it's amplified, and there's some power available for the amplifier, some bandwidth available. Noise is added to the received signal, to the transmitted signal to get the received signal, and then you demod, decode, and present that information to some sync. Okay, so this is the very standard communication problem. And the question is, at what rate can we transmit if there's a certain amount of power, a certain bandwidth, and a certain noise level? Okay, okay, and Shannon solved this problem many years ago. He showed that there's actually a fundamental limit between, or actually a fundamental trade-off between the amount of energy used and the bandwidth efficiency. Okay, so we're going to define the data rate to be R. The power is P, the noise power spectral density is N0, and the bandwidth is W. And what Shannon showed is that if the rate is less than the capacity of the channel, and this is the capacity of the channel, then reliable communication is possible. Okay, and this depends on the power level, the bandwidth, the noise, and so on. Okay. Now, what I'd like to do is convert, instead of power, I'd like to talk about energy per information bit. Okay? So if we're transmitting with a certain power and we have a certain data rate, then the ratio of power to data rate, joules per second divided by bits per second, is joules per bit. So we can replace the power by the energy times the data rate, in which case Shannon's formula becomes this one right here, which shows that what's important is the ratio of the data rate to the bandwidth, and what's important is the ratio of the energy per information bit to the noise power spectral density. Okay, and we can actually invert this expression and find that in order for reliable communications, we have to have the signal to noise ratio, the energy per bit to noise density ratio, greater than 2 to the R over W minus 1 divided by R over W. Okay, so this shows a fundamental relationship between two things: bandwidth efficiency, R over W, bits per second per hertz, and energy, energy to noise, or signal to noise ratio. Okay, and I'll show a curve of this in a second. Now, if we restrict our modulation technique to binary inputs, okay, and there's some good reasons why you might want to do that involving the power amplifier, then this result of Shannon changes. Instead of R over W less than something involving a log and the previous expression, we get an expression for the capacity region like this. Okay, kind of messy, but it still depends on R over W, and it depends on this parameter beta, which depends on EB over N0. So again, we have this relation or trade-off between R over W and EB over N0. Okay, so here's these things plotted. I'm plotting the signal-to-noise ratio in dB versus the bandwidth efficiency. And if I take the original formula that doesn't quantize the input to the channel, I get this relationship or this curve. It says I get a certain, I require a certain signal to noise ratio in order to achieve a given R over W. Okay, so if I want R over W1, I have to have this signal to noise ratio, 1.6 or 7 or something. Okay, and for binary input, this is what's required. Okay, so I cannot get any, I can't get a rate, I can't communicate a half bit per second per hertz with minus 1 dB, for example. Okay, so things down here are not possible. What's up here is possible. What's above the curve is possible. An alternate way of looking at this is to plot the R over W versus EB over N0. So I just flipped the curves over, okay? And then this is the binary input, and this is the unquantized input. The fundamental limit here is that if we want to achieve very low EB over N0, the lowest possible EB over N0 is some limit right here, which is minus 1.59 dB, and it doesn't matter whether you're transmitting binary, binary or whether you're transmitting unquantized. Okay, if you're interested in very low energy use, then binary input is just as good as not binary, non-binary. Okay, well, Shannon had a number of assumptions in his model that we'd like to relax. First of all, we have a linear amplifier, 100% efficient. Any power you put in is radiated. Okay. He talked about a point-to-point link. You've got a transmitter and a receiver, and that's it. Okay. He didn't look at any type of receiver processing energy. Okay. Normally, receivers consume energy, and so we'd like to take that into account. He also assumed that in order to achieve capacity, you need an infinite delay. Okay, so we'd like to relax some of these assumptions and see how the results change. Okay, so the relaxed assumptions are we're going to put in an amplifier that is not 100% efficient. In fact, the efficiency depends on how you operate that amplifier. We're going to assume some type of networking here. Okay, not just a single transmitter and a single receiver, but maybe relays between the transmitter and the receiver. And we'd like to incorporate receiver processing energy. Okay, so let me give you an example of a power amplifier, something that we'd like to incorporate into the analysis. These are some measurements of a power amplifier, and what I'm plotting is the radiated power as a function of the input drive power. So you have this amplifier, you drive it with a certain amount of power, you get a certain amount of power out. That's the radiated power. But there's also a certain amount of consumed power. Okay? In other words, the difference here is actually power that's wasted. It just turns into heat. All right. And you can also plot this in a different way. What I'm plotting, again, is input power, but here I'm plotting power added efficiency. How efficient are we taking is the amplifier in converting DC power to radiated power? Okay? And so you can see here that there's some input power that kind of maximizes the efficiency of converting the DC power to radiated power. So you would think you'd want to operate your amplifier where that efficiency was maximum. Yeah. Sure, sure.
So I would have thought power in, how can power in be, how can the radiated power be greater than the power in?
You have a gain. Your amplifier has some gain.
Okay.
Right. Okay. So that's the point of the amplifier, is to put out more power than it. You have the input power means the signal driving the amplifier, as opposed to the energy coming from the battery.
Okay.
So you got two places where kind of energy comes from. One is the battery, and that's where most of the energy comes from, or the power. And then you have this input power. Now, if you drive it by a different amount of input power, the signal power, then you can...
consumed power is what comes out of the battery?
Right.
The difference there is all heat or whatever.
Exactly.
Okay.
Okay. This difference is heat. Yeah. Okay, so the power amplifier is most efficient when it's driven into saturation unfortunately, when it's in saturation, you get intermodulation products. And actually, for the purpose of this talk, we're just going to ignore the intermodulation products and just think about or incorporate the part of the amplifier model that consumes heat, the heat part. Okay, and the power amplifier is least efficient when you want to when you drive it with low input power levels. Okay. Okay. Well, the second characteristics that we have to take into account is really the propagation between the transmitter and the receiver. And if we have an antenna here with some height for transmitting and a receiving antenna at some height, and there's some distance between these, then a standard model for the distance-dependent propagation is to assume that there's a direct path, and then there's this other path that bounces off the Earth, and there's some phase change here. And if you do the analysis of this received power, you get some messy formula that the received power is the transmitted power times a bunch of terms involving the height of the antennas, the distance. But for reasonably large distances between the two antennas compared to the height of the antennas, the received power is just inverse proportional to d to the fourth, the distance to the fourth. Okay, so here I plotted the received power as a function of distance for 3 different frequencies, 100 megahertz, a gigahertz, 10 gigahertz. You can see for more than 100 meters away, all these line up. And so the power received, and they follow this straight line. So the power received is just a constant divided by d to the fourth. Okay. Okay, well, if the power received is a constant divided by d to the fourth, then long-distance communications becomes very expensive power-wise. Okay, it's going to take, to double your distance, you need 16 times more power. Okay, so the amount of energy necessary to go some distance increases as the fourth power of the distance. Okay, so let's suppose we have a source and we have a destination, and they're separated by some amount of distance. And the question is, how can we get, how much energy and at what data rate can we get information from this source to this destination, taking into account that you can potentially use some relays. Okay, so we have relays that can relay the information between the source and the destination, and we would like to we'd like to find the right combination, the right number of relays. Okay, maybe we need 7, maybe 6, 5, 4, 3, 2, 1. Or maybe we don't need a relay. Okay. Okay, so I want to look, incorporating the relays, I want to figure out what is the energy usage, how much data rate are we getting through, what's our R over W, and then I'm going to define another measure called the transport efficiency. And the transport efficiency allows us, it's a single number that we can try and optimize. Okay? Whereas energy efficiency and bandwidth efficiency, you can trade off against each other, but transport efficiency is one number that takes both into account that we'd like to optimize, and we'll define it in a second. Okay, so we want to optimize over how the amplifier is working. We want to optimize over the network, how many relays should you use, and we want to optimize, we want to take into account the receiver processing energy. Now, if I go back to this, oops, let's see, go back. The more nodes I have between the source and the destination, the more energy is needed to process a signal. Every time I receive a signal, I have to spend some amount of energy to process that. Okay? And so that kind of, in some sense, drives the design toward a few relays. Okay? On the other hand, I get most efficient use out of my amplifier if I transmit in saturation. So that kind of drives the design toward, also toward a few relays. Okay? But the propagation characteristics says that the amount of power is going to decay as d to the fourth, and that drives the design toward a large number of relays with small distances between the relays. So the question is, what's the overall right thing to do in this setup? Yep.
When you mean relay, you mean just decode and forward or just amplify?
Decode and forward.
Okay.
Yep. Okay, so I've already said this. We want to optimize over how we drive the amplifier. We want to optimize over the distance between the nodes from the source to the destination. And we want to optimize over how we transmit, what code rate we're going to use. Okay, so just to give you a simple example here. We have a source, destination, and we can either transmit directly. If we transmit directly, we'll probably run our amplifier into saturation, which would be good. We get a huge propagation loss, which is bad, but we only have one receiver processing energy to take into account. Okay? The other extreme, if we go this route, we have a short transmission distance here, which is good from the propagation point, but our amplifier is still wasting about the same amount of energy into heat, or power into heat. But the propagation is good, but we have to decode and process the signal 3 times instead of just once. Okay, so for the receiver processing energy, we're just going to assume that there's some constant piece of RP called the receiver processing power that tells you how much energy, how much power is being used by the receiver. So the longer the receiver is on, the more power, the more energy it consumes. Okay, so a very short packet will consume a smaller amount of power than or smaller amount of energy than a long packet. And we're not going to, in this talk at least, we're not going to distinguish different receiver processing powers for different systems. For example, you might have a turbo code that requires a lot of processing power versus a convolutional code that might not require as much. We're just going to assume that this is fixed. And one of the reasons is that a lot of the receiver processing power is actually in the front end of the radio as opposed to the digital processing. Okay, question?
So do you assume that the transmission is kind of, it doesn't use a multi-user thing? That is, I cannot encode it so that the farther relay gets some information, nearer relay gets much more refined information, therefore I can use more power, but I can trade off between the multi-user.
At this point, no. No, we're transmitting just to one hop, and if you're further away than that receiver, then your signal noise ratio is such that you can't decode it at the rate that it was transmitted. Okay, so we're not considering anything really fancy here. Okay, so we'll assume a fixed amount of power. What we want to optimize is over the code rate. A low code rate will have a large error correcting capability, but it will also mean that the receiver is on for a longer period of time. And if it's on for a longer period of time, it means that more energy is going to be consumed at the receiver just to receive that packet. Okay. And a large number of hops between the transmitter and receivers also implies that you're going to have a large amount of energy consumption because you're going to have a large number of receivers demodulating the packet. Okay, so we're going to talk about the power amplifier and the signal model. For the power amplifier, we're just going to assume a very simple model that the radiated power increases linearly as a function of the drive power until you reach some amount of some level, and then it just saturates. And the consumed power is just the transmitted power plus some constant, which is the power that's turned into heat. And these are the specific numbers when we do some numerical results. Okay. So this is just a simplified model of the amplifier, which in equation form is given right here. The output power, or the radiated power, is the input power multiplied by some gain until you get to saturation. Okay, and the consumed power is the radiated power plus the power that's turned into heat. For the propagation, we'll assume an inverse power law. The received power is the transmitted power divided by the distance to, say, the fourth power, and there may be some constant here. Okay, the energy, we have to do a careful calculation of how much energy is used. There's energy used at the transmitter for each information bit, energy used at the receiver for each information bit, and because we're going to assume that there's a certain number of hops, k, between the transmitter and the receiver, then the total amount of energy consumed is the energy consumed in each bit at the transmitter and each bit at the receiver multiplied by the number of hops that you're going to transmit this over. Okay? Now, each receiving bit consumes some amount of power, but we're going to quantify it really by a parameter E sub p. So E sub p is the energy per coded bit that we consume at the receiver, as opposed to information bit. Okay, so if we have a coded bit, if we have energy E sub p for each coded bit, and we multiply by n, n is the number of coded bits in a code word, then that's the energy consumed by the whole code word. And if we divide by k, the capital K, the number of information bits, then that's the energy per information bit that's consumed by the receiver. Okay, so E sub p times n over k is the amount of energy used at each receiver, and we're going to have k hops, so that's the total energy used at all the receivers. This is the energy that's used consumed at the transmitter. Okay, depends on the drive level, depends on how long each symbol is, and this parameter we'll just fix. Okay, so the bandwidth efficiency, we're going to define it as expected number of correctly decoded packets end to end per channel use. Okay, so the R is the number of information bits divided by the number of coded bits or channel uses, and then P sub S is the probability of a success on a particular hop. Okay. It depends on what code we use and how much energy we use. Okay. In order for a packet to go successfully from the transmitter, from the source to the destination, it has to go through all k hops. So we have to have k successes of that packet. Each success has this probability. And then we have to penalize ourselves in terms of bandwidth efficiency for using, say, low code rates or the redundancy added to the information by multiplying by R. Okay, so this is our measure of bandwidth efficiency. And we'll use various models. We can use various models for the success probability. Each packet is successful in a threshold model if the signal-noise ratio is greater than some threshold. Okay, so you might be using capacity-achieving codes on each link, in which case this is the success probability. Okay. And this gamma here is that expression I had before that depends on R over W. Okay, or you could use some particular code, a convolution code, a turbo code, or perhaps no code at all. Okay, and I'll show you different models for actually the error probability, which is 1 minus the success probability. So if we use a capacity achieving code, and let's say our rate is a half bit per second per hertz, then the error probability is this curve right here. Error probability is 0 if you're above this threshold, just above 0 dB, and it's 1 if you're below that. Okay. If you're using a convolutional code with, say, rate 1/2, and you have a packet length of, say, 224, then this is your success probability or your error probability as a function of EB over N0. If you use a longer packet, there's actually more chances of making an error, so your error probability goes up. If you don't use any coding at all, then these are your error probabilities, packet error probabilities. If you use codes that achieve the cutoff rate, then this is the error probability curve. Okay. And for this talk, we're mainly going to concentrate on codes that achieve the capacity. Okay, so again, I have a bandwidth efficiency, bits per second per hertz that I'm getting through, number of successfully received bits per channel use or per unit bandwidth. And I have amount of energy, and there's a trade-off between those two. But in order to optimize, I need one parameter that I want to optimize, and I'm going to optimize something we call the transport efficiency. Okay, and the transport efficiency, I define it as just the ratio of the bandwidth efficiency divided by the energy used. So this is how many bits per second per hertz can you get through per unit energy. Okay, so this is what's the bang for the buck that I can get out of this system. Okay. Oh, and this depends on how many hops I'm going to use, what rate of code I'm going to have, and how I'm operating my amplifier. Okay, so for example, this is the case of just a single hop, and again, this is the capacity formula as a function of EB over N0, and here EB over N0 is not in dB for this plot because I want to show you the transport efficiency. What the transport efficiency is the point on this curve where you get the maximum slope from the when you connect it to the origin. Okay, so this is kind of, if you operate beyond this point, at larger EB over N0, you're going to start getting diminishing returns. If you operate below this point, you can increase your capacity significantly with only a very small increase in signal-noise ratio. So this seems like a reasonable parameter to use to if you want to optimize. It gives you a good trade-off between the energy and the capacity. Okay.
What was capacity? Is this the effective thing?
Yeah.
What was that?
Well, okay, so that's just the, okay, so, oops, I'm going the wrong way, sorry. Okay, so basically, if this is 1 or 0, this is, we're going to choose a rate in the EB over N0, so this is 1. So the capacity, the bandwidth efficiency is essentially the capacity of each link. Okay? Okay, so what we want to do is find, okay, the point, and this is just for the case of a single hop, the point that gives us the maximum bits per second per hertz from source to destination per unit energy. Okay, so we want to maximize, find the point, this type of point, except for multiple hops. Okay. Okay, so let me just go to a single hop and let me just ignore the amplifier for a second. Question? Yeah.
At the beginning of the talk, you show these graphs with bits, bandwidth efficiency versus energy efficiency.
Right.
Isn't that slope the same thing we're talking about? Like it was like linear at the beginning and then.
Okay, so yeah. Let me go back then. Okay, what I plotted before was in dBs. Okay, these curves.
So the next.
Okay. Yeah, this one.
Yeah.
Yeah.
So isn't that slope?
I'm plotting the same curve here. But the problem is that this scale is dB, so it kind of makes things kind of weird. Okay, so I have to, in order to show the transport efficiency as the maximum kind of slope, I have to go back to non-dB units. Okay, so this is actually, this red curve is the same curve as before. It crosses the line at minus 1.59 dB. Okay, so I'm plotting again bandwidth efficiency or capacity versus signal to noise ratio, and we know we can achieve, and this should be extended. It increases up to 1, and so this is a case where we don't assume any processing energy by the receiver. Okay? But if I start adding some processing energy, say it takes 0.25 nanojoules per symbol to process the received symbol, then I have some kind of strange things happening. Is that I get this curve like right here, which says that at very small rates, it's going to take you more signal, more energy in order to get the information from the source to the destination. And basically what's happening here is at low rates, I have long packets. Long packets require the receiver to be on a long amount of time. Okay? And therefore they consume a lot of energy because the power is at the receiver is fixed, and the longer you're on, the more energy you use. If I go up to 2.5 nanojoules per symbol, I get this curve, and then 25 nanojoules, 25 microjoules per symbol, it just increases. Okay, so this difference here is kind of how much energy is being used at the receiver. Okay, this is the red curve is the minimum energy if I didn't have any receiver processing power, and the difference is what's being used at the receiver. Okay, by the way, the 25 nanojoules per symbol, if we assume a 50 kilosymbol per second rate, corresponds to about 125 milliwatts processing power of the receiver, which is probably a little bit low relative to some things that are out there. And the assumption here is that our receiver is coherent, so that's going to take more energy than or more power than a non-coherent receiver. But
It's not much lower. It's comparable. Low power implementation for Wi-Fi is roughly 300 milliwatt. Actually, some vendors claim close to that number too.
okay, so 300 would be somewhere in between these two curves.
I think if you're doing capacity achieving code, the receiving processing power will be much more than needed in the Wi-Fi implementation.
Yeah, that would be true because you're assuming very complicated coding schemes. Yeah. Okay, and really, I think a better way of understanding this is to flip again the curves a little bit and plot the signal-to-noise ratio needed versus the rate of your code. Okay, and at very low rates, you start to increase the amount of energy that you need because what's starting to happen is that the receiver is using a lot of power or a lot of energy. Okay, so this curve down here, which doesn't increase, is the case where EP equals 0. And the difference, of course, is the amount of energy that the receiver is using. Okay, so at fairly small levels of energy, we start to get the result that you don't want to use very low rate codes because it's going to start increasing the amount of energy that's being used in total. Yeah.
Since the curves are kind of interesting and the point is 0, then you get that actually you are sending the 0 and information and then you are...
Which point here? You talking about this one here?
Yeah, the capacity goes to 0. What do you mean by capacity goes to 0?
Okay, the rate at which you're transmitting information. Okay, you can forget about the processing energy for a second. You can if you want to transmit a very low bits per second per hertz signal, you can do that. We'll say 1 bit per or 0.01 bits per second per hertz. Okay, you can do that and reduce the amount of energy you need significantly down to almost minus 1.6 dB. Okay? But if you start adding in the fact that the receiver is going to consume energy, then when you try and operate at low rates, the total energy that you're going to use is going to increase.
Because you tend to stay long, the receiver needs to activate longer.
Exactly. The receiver needs to stay on longer, the lower the code rate. Okay? Good.
For binary.
Yes, this is for binary signaling. Okay, so you might want to think that, well, maybe we should go to M-area amplitude modulation, but with a nonlinear amplifier, see, M-area would compress the amount of time it takes to transmit the signal, but you have a problem with the amplifier characteristics. You got nonlinear amplifier characteristics operating on different levels. Okay, so everything here we're doing here is for the case of binary signaling. Okay, so again, back to these curves of bandwidth efficiency versus consumed signal energy to noise ratio. And now we're in the case of multi-hop. Okay, so there's multiple hops, and here's one hop. Again, you operate at low rates. You increase the amount of energy that you need because of two things now. One is the receiver staying on long, and the other is the heat that is being used in the amplifier. And this is, for one hop, this is the point of minimum signal to noise, minimum energy usage. And this is the point where you maximize the bits per second per hertz per unit energy. Okay, since this is in dB, I can't draw the straight line because it would go to minus infinity dB, but this would be the point of maximum transport efficiency, bits per second per hertz per unit energy. If I go to 2 hops, then I can reduce significantly the amount of energy I need, and simultaneously increase the bits per second per hertz. Okay, and the red dot is the maximum transport efficiency, bits per second per hertz per unit energy, over whether you're doing 1, 2, 3, or 4 hops. Okay, so this is kind of the point we want to operate at. It maximizes our transport efficiency. Now, what's interesting, and this is the case where the distance between the transmitter and the receiver is 2,000 meters, and there's a certain amount of energy processing per coded bit. What's interesting is if we plot this transport efficiency, which is the ratio of this number to this number, not in dBs, as a function of distance. Okay, so I'm going to plot the transport efficiency as a function of distance. Okay, and this is for 1 hop. This is 2 hops, 3 hops, and so on. And what you see is that if you optimize over the number of hops, that for sufficiently large distance, the transport efficiency is just actually inverse linearly proportional to the distance. Okay? So you increase your distance by a factor of 10, your transport efficiency only goes down by a factor of 10. It doesn't go down by a factor of 10 to the 4th because of you would think because of propagation, you got 10 times longer distance. Well, if you're doing just 1 hop, yeah, you would take a big hit. But if you optimize how many hops you take between the transmitter and the receiver, source and destination, you're only going to be spending a little bit on each hop. Okay, so as the distance increases, the number of hops that you want to use, of course, increases. But this transport efficiency only decreases inverse linear. And this would be the same if we had a d to the 5th propagation loss or a d cubed propagation loss. It would also be the same if we had a different model for our amplifier. If we didn't have just a constant heat or it was some complicated function, we'd still get this inverse linear performance of the transport efficiency as a function of distance. Yeah.
So when you do multi-hop transmission, do you see other nodes transmission power as a interference or noise to the previous receiver when you do a change?
Okay, I'll get to your question in about 3 slides. Okay?
Okay.
Because this is more complicated.
Okay.
Okay, and if we look at the number of hops, the optimum number of hops as a function of distance, you can see that besides some quantization effects, you can't have a non-integer number of hops. It basically increases linearly with distance, as you might expect. And optimum code rate kind of does some weird stuff here because of the quantization. You can't have, again, you can't have 1.5 hops. But then kind of saturates at some value that is kind of surprising. It's actually pretty large, 0.96. Most wireless systems use rates like a half or a third or something like that, on that order. What this is saying is that really, in order to maximize the bits per second per hertz per unit energy, a much higher code rate is desired. Okay. And of course, what this saturates to depend. The particulars depend on what your model is for an amplifier, how much heat is being consumed, and what your is it d to the fourth or d cubed. That will change these numbers. But the fact that this is linear will remain, and the fact that the transport efficiency is inverse linear remains. Okay, so without what I call spatial reuse, which I'm going to talk about next, we get the result that the maximum transport efficiency, maximized over how many hops you use, how you drive your amplifier, what code rate you use, is some constant divided by just the distance to the power 1. Okay? And then what this constant is depends on the coding, the propagation, the amplifier. But the inverse d to the d sub e to the power 1 does not depend on that. Okay. And it also is true, this is also true, even if we use a different model for our codes. Okay, so we've been assuming that the codes achieve capacity on each channel, on each hop. But if we use some other model for the codes, say convolutional code or uncoded model, we'd still get this result. It's just that this constant would be different. Okay. Okay, so now I think I'm going to get to your question. Well, so what we've assumed before is that a source transmits the destination by relaying it through these nodes. But once a source transmits a packet and it's being relayed, by the time it gets to this node, it's going to transmit here. There's no reason that the source cannot already be starting the next transmission. All right? Okay, so this is what we call spatial reuse. All right? In fact, when he's transmitting to node 7, node 3 could be transmitting to node 4, and the source could be transmitting to node 1. Okay. However, what you mentioned happens. Okay. When node 6 transmits to node 7, he's going to obviously interfere with anything receiving at node 5, and to a lesser extent, he's going to interfere with something that's being received at node 4. And the source transmitting to node 1 is also going to interfere to an even lesser extent with what's being received at node 4. Okay? So this distance here is, if the distance between these two nodes is d, this distance is 2d. So there's some power received here that we have to incorporate into our model. And there's some power received from the source over here, but this distance is 4d. But we need to incorporate that into our model. Okay. And as you can see, if I have more nodes transmitting less power each, then I can have more simultaneous transmissions. Okay. This is what spatial reuse is all about. Okay, so the question again is, let's go back and re-optimize this system, taking into account that we have this spatial reuse. Okay, so there's some minimum hop separation for concurrent transmissions. For example, we cannot have 6 transmitting to 7 and then 8 transmitting to 9. 8 will obviously be heard by 7, and it will be the same amount of power as 6 transmitting to 7, so the signal-noise ratio will be essentially 0, not to mention the background noise. So we don't allow that type of transmission. Okay, so if there's a minimum hop separation for concurrent transmissions, and there's k hops, then the number of simultaneous transmissions is the number of hops divided by how many, the minimum hop separation for concurrent transmissions. And if we do that and account for, say, 2 neighboring transmissions, so the minimum hop separation for concurrent transmission is 3, and we account for 2 neighbors, then we get a signal to interference ratio that depends on, this is the received power due to the desired user, Okay, we have some transmitted power, some time duration, some attenuation, and another constant. This is the background noise, of course, and this is the power received from the two interferers. One was at distance 2D, and one was at distance 4D. Now, there was another one that's at distance 5D and 7D, and it just keeps on going, but at some point it just becomes pretty small, so you just ignore it. Okay, so this is now the signal-to-noise ratio in the capacity expression that we use. Okay, and we can plot again the bandwidth efficiency versus energy efficiency. Now hop 1 is way up here. One hop doesn't give you any simultaneous transmissions. Either does 2 hops or 3 hops. You start getting simultaneous transmissions when you have 4, 5, or 6 hops. And you start getting 2 simultaneous transmissions when you start having 7 hops. And again, if you optimize, if you want to achieve the minimum energy, then this would be your point here. This is the minimum signal-noise ratio. If you want to, it achieves less than 1 bit per second per hertz at some signal-to-noise ratio. If you want to maximize your transport efficiency, you can achieve nearly 3 bits per second per hertz at a slightly larger signal-to-noise ratio. Now, if I go back again and plot this, the transport efficiency here, which is the ratio of bits per second per hertz per unit energy, I can plot this as a function of distance again. Okay, so now the curves kind of change. This is 1 hop, 2 hops, 3 hops. These kind of are the same because there's no simultaneous transmissions. But as I increase the number of hops, as the distance goes up, I increase the number of hops, the transport efficiency reaches a constant rather than decreasing inverse linear. So the spatial reuse changes the inverse linear dependence on distance to a constant. Okay, so actually here's a bunch of curves showing the optimum transport efficiency as a function of distance. Okay, so this is the black curves are without spatial reuse. Okay, and let me get so this is my propagation parameter is 4. This is the transport efficiency. If it's 3.5, 3, 2.5. So all these are inverse linear for sufficiently large distance. And the red curves are with spatial reuse, and they all start out, of course, at the same place, but they end up at the same constant. Okay, so they all tend to a constant, independent of actually the propagation parameter. Okay, the optimization parameters when you have spatial reuse are somewhat similar. Again, you have a linear number of hops that's optimum as a function of distance, except that the slope is larger because the increased number of hops gives you this spatial reuse. And because that they're closer, your code rate actually is much higher. In fact, it's very close to 1 up here. Okay. Question? Yeah.
So if you use directional antennas, would you get a much better, because you won't have the worst interferer is the two hops from you.
Sure.
So if you use a directional antenna, you can eliminate that and get much better. Seems like you can get much better performance.
Yeah, except that you can only hear from one direction, right?
Yes, but you have only one receiver. Okay.
Well, okay, so I'm giving you a simple model for a network, right? Just a linear model. Okay, but reality is that the nodes might be scattered, and you would have to have a steerable antenna if it was directional. So that you could transmit in one direction and then afterwards receive in a different direction. So yeah, we didn't put any directional antennas in this work, and we didn't go to, in fact, even to 2-dimensional stuff. Okay, so which would be an interesting extension as well. Okay, so this is a comparison of the number of hops that you should use as a function of distance. This red is with spatial reuse versus without spatial reuse. And so let me summarize what we've talked about. we've investigated really the trade-off between energy efficiency and bandwidth efficiency in the wireless networks, incorporating the amplifier, receiver processing energy, and propagation and routing. And the results are somewhat surprising in that they indicate that shorter distances with higher rate codes are better. I mean, code rates on the order of 0.9 and above are what I would call high rate codes compared to what's used typically in wireless systems, which are rates a half or a third. We've done this for a simple case of additive white Gaussian noise channel, but it's easily extendable to fading and other modulation techniques. In fact, the results will stay the same, except the constant factors. But it might give us lower code rates. The result might show us that the optimum rate of coding that we want to use when we have fading is lower than the additive white Gaussian noise case. Coding really has a much more beneficial aspect when you have fading compared to an additive white Gaussian noise channel. Additive white Gaussian noise channel, you can gain about 10 dB from coding, but a fading channel, you can gain about 40 dB or more, 40 or 50 dB. Okay, so if we analyze the case of fading, I think that we would see that the rates of coding that we want to use are much lower than the additive white Gaussian noise case. Okay, but the fundamental relationship, inverse linear with distance or constant, wouldn't change. Yeah.
Do you mind go back one slide?
Sure. Yeah.
I want to look at the curve and could you comment on the average distance between hops when you go for larger distance?
Well, because this is increasing linear, what it's saying is that the distance between hops is becoming a constant.
Distance between the hop become constant or doesn't
Right.
change at all?
Well, because we only have an integer number of hops that we can do. You know, if you increase just a slight amount, you don't put another hop in there until you go over some threshold. Okay, so there's some quantization effects because we can only have an integer number of hops.
What I've observed is this: if you need to talk to a station, let's say about 30,000 meters away. This is 3 10 to the power 4. And you need about 100 hops.
No, this is 10 hops. This is 2, 3, 4 hops.
Yeah, I'm looking at actually the 100 hop basically.
Which one? Up here?
Yeah,
Oh, okay.
30,000 feet.
Yeah.
30,000 meters.
Yeah.
And that's about 300 meters, right?
Okay.
Per hop, basically.
Okay.
Per hop. Okay.
I haven't done that calculation in my head, but okay.
I observe the red curve basically says if you just have 2 stations talk to each other, these 2 stations can basically sustain a distance about 2 to the power of 2 times 10 to the power of 3.
Right here.
2,000 meters away.
Yeah.
Right.
Mhm.
So it seems when you need to talk to a guy which is farther away, you somehow need to put stations in between them much denser.
Well,
You have
I mean, there's some initial quantization effects here, but eventually this becomes, I mean, except for the integer value, is a straight line. Okay, so for large distances, beyond say this point here, this optimization becomes a straight line. I mean, if I let k be a non-integer, which isn't physically realizable, but I can mathematically do it, then this becomes a constant and then a straight line.
a straight line doesn't mean the slope is basically 1, right?
No, the slope is not 1.
Slope is not 1. It
Right.
means basically when you go to larger distance, you still get basically needs closer hops.
No, the ratio, the slope is, if I take this divided by this, that's 1 over the slope here, and that's 1 over the distance between the hops, and if that's a straight line, That means that it's going to be a constant distance between nodes. Okay, so this one would have a constant distance between nodes. The nodes here would be closer than the nodes here, okay, because of the different slope.
You have a log.
Yeah, okay, yeah, this is log, but it's still...
I'm saying this is a log, but I think only if the slope in this log curve is basically 1. I don't know. You have a constant relationship.
You don't
meaning
need one.
basically when you talk to...
You don't really need one. You need constant. I'm sorry. The slope, when you say 1, you don't really mean, you mean constant, right?
I mean this, when you have 10 times more hops, you're going to have 10 times more distance. Exactly this, basically, this is 1 unit. If you have 10 times more hops, you need, let's say, 100 times more distance. You are still having a straight line in the log domain, but the distance between hops is not going to be constant. It actually changes. Right, so basically you have 2 slopes here. The slope in the log domain of the black and the red curve may not equal.
Right, they're not equal. The spatial reuse requires a larger number, or the optimum is a larger number of hops between the 2 nodes, which means a shorter distance between each hop, and than the black curve without spatial reuse, and that's because putting the nodes closer and transmitting less power allows more multiple access transmission capability. But I still think that this means that it's approaching a constant between the hops.
Seems that applied for the black curve, which has a slope about equal to 1. That doesn't apply to the red curve.
Okay, well,
Which seems
It's a
to
log
slide.
plot. If you want the number of hops to be, you want them to be proportional to the distance, right? You're saying that it's proportional. The number of hops is proportional to distance.
yeah, I think so. Yeah,
In either case, that's what
Right.
you're saying, right? But
think so.
Jin is saying that it's not true in the red case. It's not proportional to distance because you.
okay, because the
if
slope
it's
is not
straight
1.
line on the log plot,
Yeah, okay.
then, but slope not equal to 1, then it'll be some other.
Some d to the something. Okay.
You,
Yeah,
you
maybe.
actually have
Yeah.
power.
Yeah, maybe. Yeah. Okay. Okay, so obviously what we've done is a very simple model of a network that incorporates the aspects that I think are crucial: the propagation loss, the energy at the transmitter, the energy at the receiver, the routing. But there's really many other extensions of this that really needs to be done in order to really have a full understanding of what's going on in wireless networks. You know, one thing we need to include is the MAC layer. Okay, we haven't accounted for energy that's used to access the channel. Okay, we're kind of just focusing on a single user, and that user somehow magically knows when to transmit and doesn't have to worry about or spend any energy and any bandwidth accessing the channel. So including the MAC layer in this would be of interest. Okay. We've also kind of assumed that there's this infinite density of nodes. We can put a node wherever we want. Okay. So if there is some other spatial distribution of nodes, then a node anywhere you want, then of course we're going to have worse performance. Now I think that the performance is still going to have the same characteristics, inverse, linear, or constant, but the spatial distribution will determine what the constant relationships are. Okay. Another thing that really needs to be incorporated is mobility. It takes some energy to update a routing path. As nodes are moving, the routing path changes. You have to communicate between the source and the destination a new path, And so in order to really compute the energy required, we have to include the energy required to send the messages saying what the new routes are. Okay, and another thing is we've tried to indicate what's theoretically possible, but again, we have to find practical ways to achieve what the performance limits are. And I think that's it. Yeah.
So in here, you understanding the network as a bunch of point-to-point communication, right?
Right.
So if you release this assumption, is there any work associated with similar work with this?
Well, there is work. In fact, I had a student that did some work on a two-dimensional model of a network with directional antennas and finding out what the signal-to-noise ratio is at a node, but it didn't account for routing protocols and energy. So this whole problem of wireless networks that takes into account energy and bandwidth efficiency and routing protocols and amplifiers and receiver processing, I mean, it's a very complicated problem overall. So what we try and do is figure out a subset of those that we think are important and try and understand those.
Yeah.
And then, I mean, if we can add other aspects, that's great. But
yeah, my question, in fact, is that do you think understanding the network transmission within the network as multiple point-to-point communication is the best way to go, or?
Well, it all depends on what you're interested in. I mean, I've done many things in this regard. I mean, one of the things that actually led us to here was a project we were working on, and this was for the Army, on low-energy mobile communications. And what we looked at was a bunch of nodes that were moving, and they wanted to keep track of each other's position. Okay, and they had a battery that they used to transmit information. They used the energy from it to transmit information of where they were. And when their battery ran out, they couldn't transmit where they were anymore. And so the other nodes could lose track of the node's position. Okay, so that is what we did was we tried to we set up a performance measure, which was something like the mean squared error distance that a node has about all the other nodes. We had a protocol for that in terms of how often we transmit that information. The more often you transmit it, the better position estimate a node has about the node transmitting. But the sooner he runs out of energy. Okay. So we set up a simulation of this whole thing, and we could learn some things about it, but it was nearly impossible to, well, I would say impossible, to analyze. Okay? So you can come up with models that you can simulate and get some understanding, but only a limited amount of understanding, versus analysis, I think you can get more understanding with less computer simulation time, right? Okay, so there's all kinds of approaches, and they each have their drawbacks. Okay, so this is just one of the approaches. The drawback is that the models are pretty simplified.
Yeah, but I'm trying to understand whether or not by enable people maybe to collaborate, you could get gain better than when you understand them as independently point-to-point communication. Right?
Sure,
yeah.
Sure.
So the other question is that I guess maybe I missed part of the talk, but what is the intuition that this power bandwidth efficiency, energy bandwidth efficiency goes down as 1 over D? What is the intuition there? Why not is 1 over log D or square root of D? Why is 1?
Well, the longer you have, okay, let's just talk about the case without spatial reuse. The longer the distance between the two nodes, I mean, clearly it's going to increase the amount of energy needed, or equivalently reduce the bandwidth, right? Okay, so if you say double the distance, why doesn't it go down as D squared or log D? Well, because you're going to add more nodes, okay? And I mean, you can kind of see it from Let's see if I can find my. Okay, so why is this inverse linear? Well, I mean, that's the way the optimization works. But I mean, and we can show this. I didn't go through the proof of this, but we can show this mathematically. That for larger distances, this approach is an inverse linear function. Okay. Are you going to? I wasn't done answering, but if you want to finish the answer.
I have an intuitive answer.
Okay.
Somehow, without spatial reuse, I think you have an optimal distance between the nodes. And when you increase the distance by a certain proportion, let's say we increase distance 10 times, instead of basically letting each of the nodes be more distance, you are adding 10 times more nodes.
Right. I'm just replicating the network like 10 times. Okay. Right.
This 10 times more nodes happen to basically increase the energy use by 10 times. So now, intuitively, without spatial reuse,
the bandwidth efficiency is going down by a factor of 10. The transport efficiency. Right. Right. Okay. Yep. Okay. Any other questions?
You are saying with spatial reuse, the efficiency goes to constant.
Right. I mean, in this case, there's two effects that are happening. One is you're transmitting a shorter distance, of course, between each node, but that allows you to get more simultaneous transmissions. And the number of additional simultaneous transmissions is kind of proportional to the distance. So that factor cancels out the 1 over d factor.
Right.
Okay.
We're going to go to that distance
Let's see.
the last slide before the conclusion.
This no, the last slide before the conclusion. Oh, this one, or the number of hops slide.
Probably tracking more nodes.
Yeah, I think you're right. As the distance increases, because this is a log plot rather than a linear plot, this is kind of growing, whereas this is staying constant. Yeah.
I'm trying to think if this is growing distance has anything related to the efficiency, why the efficiency is constant. I don't think that matters. So I mean, the thing is the optimal number of hops is calculated when.
Well, this is the result of the optimum number. This is the optimum number of hops that you've optimized.
I'm arguing you're using a non-optimal number of hops. You still almost be able to achieve the same efficiency.
Well, it depends on how non-optimal it is, right? And then if it's slightly non-optimal, you'll achieve slightly the non-optimal transport efficiency.
I'm arguing that even if it's
what if I use a linear model instead of this model for the number of hops? Do you think I will still achieve a constant?
Because I thought all of the curve collapsed almost to the same place.
Well, it may be possible. I haven't tried to find what the non-optimal number, or evaluate the transport efficiency for the non-optimal number of hops. But you think it also, I mean, it's obviously going to depend on what you mean by non-optimal. How non-optimal? Okay.
We'll go back a few slides and basically see. I mean, you have one slide basically shows where the optimal number is selected, not this one. This one.
Yeah.
So look at the curve.
Yeah, but they're all. I mean, if you just fix, for example, okay. One thing that you might ask is, what is the sensitivity to using the optimum number of hops? Okay, and what this curve kind of says is that it may not be so sensitive. I mean, these curves are all kind of coming out right here. They're staying flat, and where they fall off is different. Okay, so if you use a slightly non-optimal number of hops, you may not change your transport efficiency significantly. So it may not be very sensitive to using the optimum number. I guess that maybe that's what you're trying to say. Okay, yeah, that's true. Okay, as long as you're not at the point where it falls off the edge. Yeah.
Where is the point that the curve will fall off? What does
Well, all the curves. This is just we didn't plot all the curves here. I mean, this is K1, 2, 3, up to some number. I don't even know what the maximum is here, but they all fall off at some point. You're starting to go too far, and the distance between each individual hop becomes too big, and you're going to either use a lot of energy or you're going to achieve a very low code rate.
It is because the power of the amplifier model you're using, right?
Well, the propagation, mainly.
Oh, because this, if you turn me 90-degree turn, and then it looks very similar to the power curve you had before.
Okay.
Yeah, but then never mind.
This is because you're trying to transmit. I mean, these go down to 0 because you're trying to transmit too far between two hops, and you only can radiate a certain amount of power in your amplifier, right?
Saturate.
You saturate, right. Yeah. Okay, thank you.